Hi everyone, welcome to the Fast Start course for Serverless in Python. I'll lay out what this course is about, but before that I'll do a quick introduction. My name is Tony Trong and I work in the consulting industry where I've been fortunate enough to experience many domains ranging from a couple of major airlines, market research, media, and even the energy sector. I've helped found 5 startups in the past year and a half, and Serverless has been a quick and lean way to get started. As a startup, you need to move quickly but not compromise on scalability and testability as you grow. You also want to keep costs down early and not pay too much technical debt when you do expand. This course aims to get you bootstrapped very quickly and start contributing business value immediately by leveraging infrastructure as code, serverless technology, and AWS for the public cloud. Finally, don't worry about memorizing the code because the course description and this intro video will link you to the boilerplate code that has all the reusable components we build here as well as some extras. I hope this course provides you with lots of value and thank you for watching. Here is an architecture diagram of what you will be able to do by the end of the course. You will be able to deploy your serverless code in custom VPCs, segment your services in public and private subnets, and understand how to use plugins to perform log aggregation or keeping your Lambda functions warm. The reason why we structure it this way is that you can expand the number of resources on AWS. You will need to have private subnets anyway for certain services like RDS. It also adds extra layers of security if you need to be compliant. This course takes an iterative approach and each section depends on the knowledge before it. You don't have to know Python syntax as it's fairly easy to understand and read. But it does assume that you're capable enough to search for the little things and to be able to install the tooling. It focuses more on the bigger picture, and I would place the course somewhere between beginner and intermediate. So we start with the defaults like this. When a serverless application gets deployed, it uses the default VPC and you have no isolation of your functions. This is fine for experimentation, but not really maintainable or useful when you have multiple developers sharing the same space. Also, as I mentioned earlier, certain resources require private subnets. This leads us to our next diagram, where we start writing the infrastructure as Terraform code. We isolate our Lambda functions into private subnets and have replication in more than one zone for higher availability. Networking through NATs is done through the public subnets. That way our functions have outgoing egress access, but they're safe from ingress. Finally, we tackle authentication. One of the most basic things in any application is security for your users. Strangely enough, I've seen this messed up plenty of times when people don't take the proper time to really understand OAuth flows. This should be enough to structure your code and get going quickly as you build out business values for your customers. Happy watching! Alright, to get started, we'll create the My App directory. And in this, we'll create a backend directory and a infrastructure directory. The infrastructure directory will house our Terraform code, and the backend directory will house our serverless code. For the purposes of this course, we'll put the infrastructure with the backend code, but ideally we'd have them separated. Now we'll check our node version, see if there's something newer on the long-term support. We can do that with --LTS. There is, so we'll switch to 10.16.3. I've already got it installed, so we can just switch to that version. We'll check our serverless version. We've got 1.522, we'll need that later. So we'll lock down the serverless version later just to make sure that our deployments are consistent and the plugins that we use are consistent. So we want to use a newer version of Python. In this case it's 3.7. I've already got it installed through Conda, so we'll just switch to it. And then we'll initiate a pipenv environment using Python 3.7. Pipenv will make sure that any dependencies that we install are installed under this environment. So it's an isolated Python 3.7 environment. That way we don't conflict with any of the global packages. So we create our serverless template by using serverless create --template AWS Python. And that will initiate a few different files for us. These are just starter files. We'll heavily modify them in the next part of the video. What we'll do now is install a serverless Python requirements plugin. And what this plugin does is it uses a Docker container. And if you don't know what Docker is, it's just a lightweight VM that runs on the Linux kernel, but it can work on Windows and Mac as well. And what it'll do is it'll look at the pip file or requirements.txt, and it'll install all the Python requirements and dependencies that we need, package it up into a final deployable that we can push to AWS. If we look at the package.json, we can see that the serverless plugin is no more than just a node module. So in the future, we can just package it up and leave this in the dev dependencies and just use npm install, and it'll achieve the same effect. Taking a quick peek at the pip file, there's not many requirements, just Python. And in the handler.py, we're returning a status code 200 success. We'll take a more detailed look at this later. The more important file to look at here is the serverless.yaml. And this file defines everything that we need to do in the serverless framework. Plugins, provider such as AWS, GCP, Azure, and our framework version. It's highly recommended that we lock down the framework version. If the framework version changes, or if any dependency version changes ever, it's just pretty bad practice to not lock down the version, because you could get a breaking change at any moment. We'll just plug in the version number that we got from the serverless install last time. It's 1.522, and we'll accept anything before 2. We'll also modify the Python version to match our system version, so 3.7 instead of 2.7. We can also see here that the function is defined as hello. And we'll just kind of remove all the commenting, and we'll heavily modify this file later. And we'll do it in such a way that it can scale out as your application gets a little bit larger and it becomes a little bit more readable and maintainable. If you leave everything in the serverless.yaml file, it can get rather unwieldy and large. We'll start with moving a customs.yaml file outside. And instead of putting it inline, what we can do is say customs and use a special syntax to reference an external file. Let's call it resources/customs.yaml. So we'll create a resources folder here and put our customs in there. What the framework allows us to do is, when we reference these external files, especially the custom tag, it allows us to put in configurations for plugins or put in our own custom variables. We can also build our own custom plugins as well. You'll see more of it later when we put in custom variables based on different environments. Our plugin requires some configurations to be set, so I'll just paste that in. And if you notice that there's a Dockerize pip element, we can set that to either Linux or non-Linux. If you're running on Windows or Mac, just set it to non-Linux. And the last thing we'll do here is deploy the application. So I have a virtual MFA device set on AWS account, and what I'll need to do is sign into it using AWS MFA. I've set up a profile in my .aws/credentials file or config file, and set a profile called personal, where I have my secret access token and secret key. Right now I'm using Authy on my smartphone to put in the authentication code. And what that will do is it'll go hit AWS and it'll give me a temporary token which I can use. It'll expire in about a day or so. AWS MFA needs to be run. If you don't run this and you have a virtual MFA device set, the application won't deploy. So all we have to do is run serverless deploy. The default stage is set to dev, and in this case stage and environment are equivalent meanings. So we'll let it run. At the moment, it'll put everything in the default VPC. What we'll do later on in Terraform scripts is put more security best practices into play and find a way to isolate our application just a little bit more. It's more important if you have a shared environment with other developers. But in general, it's a good practice just to isolate your applications and functions. And we'll need those VPCs and subnets anyway if we're going to deploy a Postgres database or some other services that need to sit behind a firewall. If you look carefully at the terminal, you can see that it's pulling in a Docker image called lamci/lambda build Python 3.7. That's our plugin at play, so it's pulling down that Docker container to build our dependencies for us. Once it's deployed, you can see that it outputs our service name, our stage, the region that the application sits in, and we can execute a serverless command to invoke the function. At this point in time, we don't have any RESTful endpoints yet, but we'll do that in the next section of the video. Let's restructure our folder a little bit so that we can add some customizations and scale it a little bit easier. We don't want the serverless.yaml file to get too large, so let's start with setting the stage to explicitly be dev. Even though that's the default, we just want to make sure that it's very clear. We'll set our region to AP Southeast 2, that's in Sydney. We'll make the default memory size of the Lambda functions to be 128 megabytes. You can override this in each individual function, but it's good to set the minimum size. Then what we'll do is set some common environment variables for each Lambda function. These will be injected into the Lambda function themselves, and because we're in the provider section, it'll be for every single Lambda function. You'll see me use some special syntax here for the region, so we can self-reference previously defined tags such as the provider. And this allows us to inject dynamic variables in. For the log level here, we'll actually reference a custom element and at the same time reference the stage. So if the stage changes from dev to staging to production, it'll pick up the right log level. And we'll see that a little bit later when we modify the customs.yaml file. Another important element to consider is tagging all of our AWS resources. And if we do that under the provider tag or element, we can add in the tags element, app name, stage, and owner. That way, when we go on the AWS console, or any of our colleagues go on the AWS console, it's very clear and it's very visible to see which functions belong to who and what stage they're in. I'm just going to quickly fix up these colons here. They should be dots. What we'll do next is specify an external package.yaml file, and this allows us to specify what goes into the final distributable. There are certain files that we don't need for the Lambda function to actually work. The package.json, node modules, any readmes, the infrastructure code itself, that can all be removed. And then the external resources as well. Resources are AWS resources in this case. The only thing that we're going to specify is the default API Gateway error responses. By default, API Gateway does not return the proper CORS headers for cross-origin requests, so we need to specify the allowed origins. And in this case, we will also specify external files for one specific function. We'll go into more detail on how to refactor the function in the next part of the video. You'll notice that I've added the API Gateway errors.yaml, the package.yaml, and now the hello.yaml as placeholders. One quick thing that I do need to do is change the stage environment variable earlier. We switch that to the custom.stage. What that does is in the custom.stage, it looks for the default, the option in the command line. If that's not there, then it'll use dev as the default. As mentioned earlier, we'll add in the files that we want to include and the files we want to exclude here. IDE files, git ignores, readmes, and we only want to include the hello directory, which contains our function. We'll need to do that for every single function that we specify. For now, it's just the one. What we'll paste in next is the default API Gateway response errors for 400 and 500 cross-origin requests. If we don't have this, the browser will return a not allowed cross-origin request error. Lambdas on AWS suffer from a cold start problem when they haven't been executed in a while. So before they've been allocated resources on actual servers by AWS, the API Gateway might return that error. Once the Lambda has been warmed up properly, then we shouldn't get that error anymore. As we prepare for our bigger application, let's change the hello.yaml file into a user profile. So we'll call this profile.yaml. Ultimately, what we want to set up is some kind of user login using Cognito and have a little bit more complexity in our application, just to demonstrate something a little bit more concrete. The previous deploy was a simple function that just echoed something back, but we actually had no way to invoke it. What we're preparing for now is a RESTful API. And this is just one way of organizing that I found to be quite scalable and useful. I like to create one folder per function or a folder for a group of functions. And what we'll do is move the profile.yaml under the profile folder and call it main.py. You don't have to call it main.py, but I found naming it this way rather useful. We also need to add in the init.py. This tells Python that it's a module so that we can include it in other functions. You also need the init.py in order to execute it as a module. So on the command line, we can execute these locally. So let's rename the function to getProfile, and we'll reference the profile folder, the main.py file, and the method we're going to execute. We'll also call that main as well. We need to attach an event to API Gateway to tell us how do we execute it. Basically the RESTful endpoint. So that's going to be an event, and the type is HTTP, and we should define the path. So let's call this profile and the ID in the path. The ID is a URL parameter, and in the curly braces it's kind of a placeholder. The method that we're going to do is a get, and we're going to enable CORS just by setting it to true. So we want to make the ID a mandatory parameter, and we'll just do that with request parameters and paths. ID should match up with the parameter true. And the reason why we do this is because then the URL looks a little bit nicer to read than setting a query parameter. So we'll modify our function now and change the method to main. We'll put an empty placeholder in there for now. Just do an empty return. And we need a way to execute this locally. So we'll go if name equals to main, then we'll execute the main method. And we'll put in empty arguments for now. The event and the context arguments actually come from API Gateway. So when we execute it with curl, it'll give us information about the arguments, things like the context ID, if there's any headers, things like that. The body also sits in the event. So let's execute this on the command line to make sure that it works. We'll run this in pipenv. And we're going to run the Python command, which will execute Python 3.7 and profile.main. Profile is the folder, main is the file that we're executing. And it'll run the if name equals main part. Cool. The function as it is now won't actually return properly if we deployed it. What we need to do is return proper HTTP status codes and a proper JSON response message. We can also return an empty response as well with just a status code. That's perfectly valid. Since we're going to be doing that fairly often, let's make an API folder. And we'll make it a module with an init.py. And let's call it responses.py. There are some common headers that our Lambda functions need to return, so we'll just specify that here. So you need to specify the access control headers to enable CORS. Without it, it would actually return an error to the browser. So we import HTTP status. And we specify our content type as application JSON as well. One way to return properly is just to return the status code as mentioned earlier, but we still need to provide our headers. So let's go ahead and do that. So the generate empty response method just takes a status code. We can either pass one in as an HTTP status, and we pass the course header. The other thing that we can do is pass in a JSON body. So we just make a generic method called generate response, which takes a body, and we'll just turn it into a JSON object by using json.dumps and the status code. We can reuse our generate empty response function to include the header as well. The OK response is the exact same thing. It's just a shortcut. It takes a body, but it returns an HTTP OK, just as a convenience function. So I think you get the idea now. We kind of reuse everything, and let's put in some common methods for errors using the generate message response and generate empty responses that we defined before. So these are just nice helper functions that I hope you find useful. Let's use what we just created in the profile function. And first thing we'll do is include our function. So we'll import from API.responses the OK response function. Remove the print. And let's call our function. We'll return the body as just a hello message. So it just takes a Python object. All the key value pairs, as you recall, will be JSON dumps into a proper JSON string. Just say hello world and the message. And then one last thing we'll need to do is include our new API and our profile function in the packages. Okay, so we're just about ready to deploy. What I'd like to do next is actually go through some error scenarios where something might not have gone right. So the first thing is our serverless version. Right now I'm using my system's default node version, which is not the one that we were showing earlier. So what you'll see is that there's a framework version mismatch because the serverless framework version that I have installed on this node version is not the latest version on the latest node. So here we'll do a serverless deploy. And you'll see that we'll get a framework error. So my current node version has an older framework installed. So we'll switch our node version to 10.16.3. And this node version should have the proper serverless version installed. Let's do another serverless deploy. Again, we get another error. So what's wrong this time? So we've got two errors actually, but we'll address the first one. So we're missing a config. And we need to add in the log level. The second error we'll address is the MFA. So previously I mentioned that if we didn't sign in with MFA and we have virtual MFA enabled on our account, it wouldn't work on the deploy. So we'll use our personal profile again. After signing in, we'll do a serverless deploy. And everything should be fine. We'll grab our URL. You'll notice that there's an endpoint now that we can actually hit. Just run a curl on that. We should be getting a hello world message. Let's take a look into the AWS console to see what actually gets uploaded into S3. The bucket gets automatically created using the app name that we defined earlier in the serverless.yaml file. Generally, I don't even take a look at this, but it's a good idea to check it in case you're not sure what actually gets uploaded. In case you're using a plugin that has issues or you're not sure what's actually in there. So the CloudFormation template JSON contains the resources and definitions that actually get provisioned. And we can take a look into CloudFormation itself. CloudFormation just defines all the different resources that we want to use, and it's usually done in very large JSON files. So the nice thing about the framework is that it does all this for us. But by having the CloudFormation here, you don't need to maintain state across machines. That means anybody who's running the source code can actually deploy, and it'll take a look at this CloudFormation. The only caveat there is that the backend application name needs to be the same. Otherwise, it can't find the CloudFormation template. After we take a look at the defaults here, we'll write some Terraform scripts so that it supplements our serverless code. It's good to establish a baseline though, so we know what we're dealing with. Alright, so let's take a look at some of the networking. First thing we'll do is go into VPCs. And a VPC is just a virtual private network. It's a logical separation of where AWS resources go into. We've only got one in this case, which is the default one. And it's kind of open to everything at the moment. Then we'll take a look at the subnets as well. In this case, we've got 3 different subnets. And a subnet is just another way to section off the VPC, which has a larger list of IP addresses, and we'll break them into 3 different networks. We'll do more of that later when we hit the Terraform scripts. So there's no network gateways, and there's one internet gateway so that there's outgoing access. These are the security groups. We can see that it's still the default VPC that it's attached to. And then we'll take a look at API Gateway. So API Gateway is the entry point. It sits between the Lambda functions and when we actually invoked it through the terminal. And we've got our profile function, and it takes 1 argument. We'll open that up in another tab and come back to that later. So we can see that you can test the function here if you want to. It's just good to take a look, but we're not really going to use anything in there. And then we'll go into our gateway responses and double check that our 400 and 500 defaults have the CORS header responses. Now in production, we'll change the asterisk to whatever domains we want to support. Our Lambda function, here we go, it's attached to an API gateway, and it's the security group and the IAM roles give it access to write CloudWatch logs. When we execute the function, if we want to see what kind of outputs it has, any errors or things like that, we go into CloudWatch. And we hit logs on the left-hand side. So here's our Lambda function. I'm going to hit the endpoint real quick to just generate some logs. And hit the refresh button. From the time you actually invoke the function and when you actually get the logs, there's a slight delay. So just refresh just to see what's happening. So you can see the request ID and how much you're billed for. So it took 100 milliseconds to run, and it's 128 megs. So that's it for the logging, and we'll improve upon this methodology in a little bit. Okay, cool. Let's take a look at what gets deployed today. The functions get invoked through API Gateway. They sit on a default VPC and a default public subnet. They can make outgoing calls because it goes through a router and internet gateway, which is attached to the default VPC, and all logs go through CloudWatch. where we want to end up is something like this. So all calls still go through API Gateway. We'll create a new VPC and 2 private subnets. So the functions get replicated into the both subnets. Logs still get pushed to CloudWatch, and all outgoing internet connections go through a NAT, which sit in 2 public subnets and go through an internet gateway. Now, the good thing about putting the Lambda functions in the private subnets is that if we have more AWS resources, such as Postgres server, MySQL server, or something like that, they're actually required to sit inside private subnets. So for the Lambda functions to access those resources, they need to sit in the private subnet as well. Then we have an increased level of isolation, so there's more security. So one last thing to do is refactor our get profile function here. Instead of returning an OK responses with a static message of hello world, let's actually return the path parameter. So let's remove this. And we also want to do some error checking, so we'll return an error response if there's an improper request. So the event that API Gateway will bring down has the path parameter in it. So let's just set that to path params variable. And we return none as a default if it can't get the path parameters. So the path parameters are empty, we'll just return with an invalid request. Then we'll extract the user ID, and that's just in the path params. We'll just do a get as well. And similarly, we'll do the error checking. Now when you return a custom object, that just returns whatever ID was passed in. And we can do that with the OK response. We'll call that user object. And if you recall, what we're going to do is just JSON.dumps it in the OK response method from the previous video. And we'll echo the ID. Cool. So now we need a way to actually execute this locally. We can simulate an AWS API Gateway response, an event here. And so we'll create an event and we'll give it a path param element. We'll just call that test ID or something. So when we run this locally, we can just test it as a smoke test. If you wanted to write unit tests, we can, and we just use the mocking library that's built in. We can write one of those later. So what we want to do next is actually declare how to deploy the Lambda functions into these private subnets and VPCs that we saw earlier. So the first thing we'll do is go to our serverless.yaml file. And under provider, we're going to use the tag VPC. This is built into the framework. And in order to specify the VPC, we actually need to give it the VPC's security group ID. We'll get that from the output from Terraform in a bit. The difference is in the subnets, we are going to have 2. And we put in the subnet IDs. So not the security group IDs for the subnets, just the subnet IDs. That's a very important factor for the framework. Okay, finally we're ready to move on to some actual Terraform files. First thing we'll do is go to the infrastructure folder and actually put some placeholders in. And we'll create a main.tf, an outputs.tf, and a variables.tf. This is kind of the standard practice, Variables.tf contain variables that you would actually put in to substitute into the Terraform scripts. The main.tf file is where we'll use most of the modules and write the Terraform code. We can also write them into various different files as well, and Terraform is smart enough to do the proper order. And outputs.tf will be what we want to display at the end when we finish running the script. So first thing we'll do is lock down the Terraform version, as with everything. We can even specify an external state, and when you run the state, it needs to know what AWS resources you've provisioned and how you've provisioned it, so that next time it can do a diff. By default, it'll store the state on your local machine. The provider tag is the public cloud provider. Terraform supports many public cloud providers such as GCP, AWS, and Azure. And we can specify a version here. We can also specify an external credentials file, but we'll just use whatever is built into our system. Next, we'll specify a module. We'll call it VPC. A module is kind of like an instance of what we're using. And in the source, I'm going to specify an external resource. This will be Git or another repository. And the module happens to be called VPC AWS. I'm going to lock down that version as well. We can build everything manually and by hand, as we saw earlier in the diagram, but this verified module will save us a ton of time. So I'm just going to open up the Terraform registry where we can see where this module lives, just so you know what I'm talking about. I'm going to search it up real quick. Don't remember where it was. And we go into the registry on Terraform by HashiCorp, of course. I'm going to search the modules called VPC. And we're looking at AWS and verified modules. So the module does a lot more than what we're using it here for, and it lists very clearly what inputs and outputs you can get from it. So if your architecture is a little bit more complicated, this can help you with that. Okay, cool. Now the next thing we want to specify for our architecture is just set a name. In this case, we're going to reference a variable now, and it's going to call it project. And the workspace. The workspace is kind of like the stage or the environment. So if you wanted like a dev, a staging, and a production environment, you can dynamically allocate those resources here and switch between different workspaces. I'm going to create an external view of the variables file. So as I fill in the variables, you can see what I'm referring to. And in order to refer to a variable, you just go var.project. And so we have to declare the variable project in here. Give it a description. We can also give it a default variable, but we won't. A default value, but we won't. So when we run Terraform, it's going to ask us and prompt us for what that variable is. Next thing I'm going to do is the CIDR range. This is a networking term, and what we want to do is in our VPC specify how many IP addresses we get and what the default IP address is. Here I'm going to specify some networking commenting. In case the variable files get large, I like to do a little bit of commenting in there. So we declare CIDR. And let's go with a reasonable default. So in this case, I've chosen a very popular one, 10.0.0.0 and /16. So /16 are the most significant bits first. So an IP address is a set of 8 bits, and we're going to use the first 16 bits for networking. And then the rest are the actual IP addresses available to us. It gives us 60 something thousand, I think, from /16. We can use an online calculator for that. So here I'm going to highlight the first 16 bits. That's what we're going to use for the network part, and then the last 16 bits for the IP addresses. So that's all that shorthand means. That entire range is for our VPC, and our subnets will take sections of that VPC, that range. So the availability zones is what we're going to specify next. And in the Sydney region, there are 3 zones, A, B, and C. We won't use all 3 zones, but we'll specify a couple here. Let's go with A and C. So AP Southeast 1A, or sorry, 2A, and AP Southeast 2C. We can also create another file called something tf_vars, and those contain secrets and they fill out these variables. But because we only have one dynamic variable, we won't make one of those files. So the next thing I'm going to do is specify the private subnets. This is also another CIDR range, and I'll explain that in a little bit. If you recall, there's going to be 2 private subnets and 2 public subnets. And subnets are just another logical grouping of resources. The thing you do have to be careful of is when you allocate these subnets that they have a limited number of IP addresses. So you're going to either need to make more subnets, or you're going to need to allocate the right number of IP addresses when you do your subnetting. Okay, so we declare the variable private subnets. And a reasonable default is going to be about 256 IP addresses. So if you remember, the first 16 bits are part of the network, and then the rest, we're going to split the rest. In this case, I'll just go 10.0.1/24. And then the second availability zone is going to have the same amount of IP addresses. I'll do the same for the public subnets, but give them a slightly longer range. So instead of 0, 1, it's going to be 101 and 102. In case I wanted to make more private subnets later, I can go 1 up to 101. And the maximum number there is 255. This module also requires enable NAT. By default, it'll create 1 NAT per subnet. There are other configurations in this module, such as 1 NAT where they all share, but I would prefer to have 1 NAT per subnet just for scalability reasons. And this is just a Boolean variable, so we'll just set it to true. The default is true anyway, but I'd rather be explicit about it. And then the last thing we want to add in is some common tags. So when AWS creates these resources, we can see these tags. That way we know, again, who owns what and what is automatically managed versus what is created manually. In the environment tag, I like to stick in the workspace. So if we switch workspaces or create new workspaces, it'll deploy an entirely different set of resources for us. That way we don't have to duplicate our code for each environment. To initialize our Terraform project, we need to run Terraform init. Here we get an error because I actually misspelled the VPC AWS module. And that's the error it gave us. So we'll go back in and change this up. So it's VPC/AWS. And keep in mind this module is called VPC. We'll need to remember that for the outputs. Do another Terraform init. And what it'll do is it noticed that we use the module. It'll go and fetch that from the registry and store it on our local machine. If you recall, we needed to fill out the output.tf file. In our serverless.yaml, we needed the VPC security group ID as one of the arguments and the subnet IDs as well. So to address data from AWS resources, we can use this data element and apply a filter on it. And what we'll do is get the module VPC ID and put it into the filter. So there, module.vpc, VPC was a name that we were supposed to remember earlier, and .vpc_id is one of the output variables. To actually use it, we actually need to specify an output element. We can give it any kind of name, and the value will be what the data filter output will be. And then the private subnet IDs. And here, I was going to output the AWS region as well, but we don't really need it. I'll go back and fix this later, but this doesn't really affect the Terraform code. Okay, then what I need to do next is declare a new workspace. And we do that simply by typing Terraform workspace new and the name of the workspace. And a workspace, in this case, I just use it as the environment or the stage. Those three terminologies I'll tend to mix up interchangeably. So Terraform workspace new dev. And in order to see what resources actually get made, we can just do Terraform plan. I'll just call it my app. It will prompt us for any variables that we didn't put a default value for. So if we scroll up here, we can see that all the pluses mean that it's going to create all these new resources. So there's a security group. Some of them are calculated after the resource is made because we don't know what they are until AWS generates them. And the module does a lot of work for us. It's going to create an elastic IP for the NATs, and it's going to do all the routing. It's going to put in the internet gateway. And if you notice that it does all the tagging as well. Some of the elements have a timeout, so we can time out at 5 minutes if there's an issue. If the resource is taking way too long to create, there might be a problem. So those are route tables. And Terraform is smart enough to make the resources, if they depend on each other, in the correct order. It's also best practice to put all the resources in a linear fashion in your folder organization. All right. Do Terraform apply? And we actually have to say yes. It's going to ask us for the project name every time. We can, like I said, use .tf vars file. That won't get asked, but we need to store that somewhere safe in case we have sensitive information. But here we don't. So let's let that run, and we'll be back when that completes. All right. Now that the Terraform scripts have run, we see the outputs here. So our filter on the VPC ID, and the VPC ID being that large number VPC-008D7, and the IDs that we got back was this thing that starts with SGs for security group. We'll copy that and put it into the serverless.yaml file. Just correct this from earlier, just remove the data element that I'm not using. Okay. Just paste in the security group. That way serverless knows to associate the Lambda functions with that VPC. I've tried putting the VPC ID in here in the past, but that doesn't work. And then I'll just go and fetch the subnet IDs. These are the private subnet IDs. None of the Lambda functions go in the public one. Okay. You notice I switched node versions to make sure that I'm using the latest one. I'm going to do a serverless deploy now. Switch to the right folder first and then do a proper deploy. And I'll let this run and then get back. Okay, we're now back. And we have a different endpoint. What I've been doing is been deleting the stack and recreating them. So now we've got the curl results. And our path parameter is an ID. I'm just going to put in a placeholder ID called my ID. It doesn't really matter. This is the startup time that I was talking about. It took a while, but it echoes back the user object with the ID that we're expecting. I'll put in another one just to populate the logs. Okay, so the second time was a lot faster. Let's open up AWS console to see what's actually created. So first thing we'll do is go into VPCs. We should have a new one. So there's two now in the default subnet, or sorry, the default region. You notice that the cursor is a little bit off because I've cropped the browser a bit to hide some sensitive information. Okay, so we've got the new VPC. We can see the CIDR is an IPv4 address, 10.0.0/16. And all of our tagging is there. Great. Next, we'll take a look at the subnets. So we should have 4 new subnets. There's the 2 private ones and the 2 public ones. They're both in 2A and 2C. And the VPC ID on the right hand side is the new one. Took up the route table, see where the traffic goes, and here we've got the two NATs. The two NATs sit in the public subnets. Okay. And here are the route tables. So the routes for the private subnets go straight into the NATs, and the public ones just go straight to the internet gateway. And our new internet gateway for that VPC. Okay, so let's take a look at our Lambda function to make sure that everything's okay with it. Get profile Python 3.7, API Gateway resource. You can actually see the code from there, what was packaged with it. Our environment variables. Our tags. And here it should be the important part here. So our new VPC ID and the two subnets they belong into. Cool. Everything seems in order. Now we have a isolated Lambda function. It's replicated into availability zones, and it can access the external internet. Any resources that require to be in the private subnets can be accessed by this Lambda function. So this is our application so far. Our web app or curl will go through API Gateway. It then invokes one of the Lambda functions sitting in both private subnets, which sits inside a VPC. Unfortunately, right now it's public, so what we want to do is add a little bit of authentication. AWS provides a service called Cognito, and inside Cognito it has a user pool. When users register for our service, they'll create an account on the user pool. The pool does things like register the user and does a verification through email or phone number. It'll send an authorization code. So the way this works is when the REST call goes through API Gateway will execute the authentication function. It does so through JWTs or JSON Web Tokens. And if the authentication raises an error, then it's an invalid request. If it returns true, then it'll actually execute the getProfile function. Some other alternatives to Cognito are Okta or Auth0. But since we're using Terraform anyway, and AWS here, we'll just put it into our Terraform scripts. Pricing for Cognito is pretty cheap early on as well. We only pay for the users on our pool. We don't pay for anything else. Okay, so here's our Terraform code. Well, here's all of our code really. And what we're going to do is create cognito.tf. And our infrastructure code. Just move it over here. There's enough separation that it warrants its own file. There's quite a bit. It'll take up the entire screen really. And on the right side we'll have our variables. We'll add some stuff. So I'm going to explain them one line by line. Might not necessarily type them out line by line, but I think it's good to have an understanding. So our first resource is called AWS Cognito user pool. We'll just call that user pool. And we need to give it a name. If you recall, I like to use Terraform workspaces for the different environments. So it's going to be the project, the workspace, and I'll just call it the user pool. Fairly standard format. Next thing we want is a count. And it goes off a variable called enable cognito user pool. So what this does is we don't necessarily always want a user pool. And what I've done here is do an inline if statement. If there's a user pool or if it's enabled on the Boolean true, then we're going to set the count to 1. That means for this resource, we're going to have 1 instance of it. If count is set to 0, then we won't have a user pool. So we'll use this for a couple of things. And by default, we'll have false. There's one thing to be aware of. Whenever we use the count object, it's not easy to refer to the resource or the properties of the resource when we need it for outputs and things. I'll show you a couple of functions later on how we can address that issue. So let's continue. So the next thing we need to set is the properties that we want to collect. So in this case, alias and preferred username. And what we want to do is have Cognito verify the email for us. So we're going to use that attribute. If we were collecting phone numbers, which we can, Cognito will send an SMS with a verification code out if we choose that method. But in this case, we'll use email. So I'm going to use another variable here called verification subject. This will be part of our emailing template. So when Cognito sends out the email, this is the actual subject. It's going to have our project name, dash, and the subject, which we'll add into the configuration. So we haven't used this variable type before, but it's called a map. It's just a nested object, so we can group related ones together. Create the variable cognito config. Types equal to map. And the defaults. So the first property that we're going to add in is the subject. Just say device verification code, just for demo purposes. And then we need the body as well. Let's add that in here. So for Terraform, it's no verification message. It'll be under the same config, but a different property, different key. and verification code. And then there's a special placeholder, which is 4 hashes inside of curly braces. Cognito will inject the verification number inside this placeholder. And the last thing to do is to tell us to use the template. And we actually want to tell the template to use the verification code type code. So final config for this one, default email option. Confirm with code. You can check the different types in the Terraform documentation and the AWS documentation. Okay. Now we want to add a password policy. This is for users who sign up. These are fairly self-explanatory. Minimum length requires all sorts of stuff. Lowercase numbers, symbols, and uppercase. Make it a fairly strong password. There's another option to enable multi-factor authentication as well, but we'll skip that for today. You can just look it up in the documentation. And the schema for the email property. It's a string, it's called email, it's required. And the email has to have a minimum length of 7 characters, so that's a fairly short email. Max of 32. To close it out, we'll add some common tags just like we do for other resources. That way when we bring them up or delete them, we know who it belongs to. So our application requires a user pool client. The client identifies which application is using this pool. You can have more than one use the pool, but for our backend code here, the user application will create one specifically for it. Do that with the resource and user pool client. User pool client. And we only want to create this if we have Cognito enabled. So we name it the same way. And we'll create accounts for it as well. Let's copy that from the top. Okay. Now we need the user pool ID. And like I mentioned before, it requires a special syntax because we have the count. So we do a join. So we're joining nothing to the user pool, and the asterisk there means take everything from the user pool list. Because we have a count, it's a list. But because we only have one item in the user pool, it's going to join it with an empty item, and we just take that default value. So that ends up being just the user pool. So we're not going to generate a secret. In order to use this user pool, just set it to false. So clients can opt to generate a secret, and Terraform will output a secret. But that means you have to pass that secret onto every call that you make to the Cognito user pool. And we disable SRP auth. SRP is secure remote password. It's a way of authentication without sending the password over the wire. In this case, we'll just set it to no. It actually requires a lot of work to do that. So what we're going to do is rely on HTTPS, so the TLS certificates through the browser to handle the encryption for us. So when we authenticate, the password would go through the encrypted connection, just like everything else. And then we'll set the allowed OAuth flows. The OAuth flows can be implicit, code, any of the OAuth 2 flows. Here I've called it allowed OAuth scopes, but I think in hindsight the better variable name would have been flows. So to set the variable OAuth flows default. And let's assume that it's a SPA app that's purely JavaScript. So the new recommended method is to use the code OAuth flow. I recommend you look that up to really have a good understanding of this if you don't already. And implicit. This is why we didn't bother with generating a secret, because you can't hide secrets in pure JavaScript code, especially for all the new front ends. Okay, we just set allowed OAuth flows to true. If you recall on the OAuth 2 flow, code means once the user authenticates, they get a code back and they exchange that code for a token. And implicit, after they authenticate, then they get the token immediately. Now the callback URL is once the user logs in, they'll get redirected back to your website, and you can set that to whatever your domain is and the callback. The callback will contain either the code or the JWT token. Then we set the supported identity providers. In this case, it's Cognito. This is where you can set it to Google, Facebook, or log in with Amazon. Then we set the allowed OAuth scopes, OpenID and email. That means in the JWT, and then the claims we're allowed to access the email. You also need the OpenID to be ticked off in order to get access to like the sub and all the other claims. Okay. Now we need to set up some outputs. We need the client ID that gets auto-generated and the user pool endpoint. We'll need that for our backend application in order for it to work. Here we use something else called the element and concat function built into Terraform. So it's just selecting the first element at a certain index. So the index is 0, so the first element. And concat is we're taking the entire user pool list again. And the asterisk represents everything. We combine it to an empty list, and we take the first item. We have to do this again because of the count object. There's no easy way to do that in Terraform. It's a requested feature. But until it's there, we have to use this kind of hack around to get that. We don't necessarily need the ARN, but here I just like to output that as well. Okay, now we can do a Terraform apply once we have everything that we need. User pool, client ID is the last thing. And we'll be right back once we do an apply. These are the results of our Terraform output. You'll notice that there's a new VPC ID and a couple of new subnet IDs as well. Don't worry about this. That's because I've torn down the stack and brought it back up. In the code, if they don't match up, don't worry about it. I'll actually replace them as we go along. Now you'll notice that there's the Cognito endpoint for the front end and the pool ID. And we also have the app client ID for our application. We need this later for our backend code in order to actually verify the JWTs. To start off, we'll create an auth folder, and it'll have a couple of different files in it. The first one being a utils.python file, and what this houses is common functions for our verification code. I prepared this earlier, so I'll just paste it in and explain it line by line. Don't worry about memorizing the lines because the template provided on GitHub will have this code for you. Okay, so Cognito does JWTs for authentication using OAuth flows. And you notice that there's a key URLs variable in there, and it takes a placeholder region. That's the AWS region and the user pool ID, which we had earlier. We'll pass those in a little bit. So the common functions are get known keys and verify and get claims. And we can take a look at what the keys look like. I'll paste in an example here. AWS posts known keys on a public URL given this template. And a key can have more than one item in it. So it tells us the algorithm that was used for encryption or encoding and the ID. In case they cycle out the different keys, they have more than one, so one of them can expire and you use the other one. So that's passed to us during the headers when a request is made. And we just look up the key ID. Okay, the region, the user pool, and the well-known keys. You can find that in the documentation. So we load the keys and we read them. Cognito uses a private key to generate the signature for the JWT. We can verify that with one of the public keys on the known URL. So what we do here is get the token, and in the Cognito event, we just take that from the authorization token element and we split it with a blank. And we loop through the keys that you see on the right hand side. It's an array. And we search for the proper key because we'll need to know what algorithm they use. In this case, for example, RS-256. If we don't find the proper key, we return false, and that will raise an authentication error. Then we construct the keys and we split it. So the token looks like a bunch of base64 encoded things with a couple of dots in between. Then we get the unverified claims and we compare the digest. So comparing digest is just checking the client ID claim and making sure that this Cognito pool is what our app is using. And compare digest, make sure that we're protected against timing attacks. There's a get sub function. You can see that it takes it from the request context, the identity, and Cognito authentication. So these are convenience functions that I've included. It's all pulled from the documentation as well. The sub is also the user ID. And then you've got the generate Lambda policy. So this generates a policy, an AWS IAM policy. If we've properly authenticated, what we're going to do is generate this policy so that the actual function we're trying to call, in this case get profile, can run. So we generate an allow policy and say that, hey, you're allowed to execute or invoke this function, as you can see in the action execute API invoke line there on line 69. Cool, so these are our utilities, and what we'll also need to do is create something that uses it. We'll create bearerauth.py because we're using a bearer token. And this function is fairly straightforward. I'll just paste it in. Okay. So we see the environment variables where we pass in the user pool ID and the client ID. And the keys are using the utils function getKnown keys. We check our claims, and if the claims are false, or anytime we return false in the utils.py, we raise an error unauthorized. And that will actually return an unauthorized error. Otherwise, we generate a Lambda policy. So for that user, which is in the sub, we say allow and run this method. Cool. And we need to create the environment variables for their pool ID and the client ID. It's going to pass it for every single function. And you may have more than one user pool, so we're going to put it into our customs.yaml based on the stage. If we change the Terraform workspace, we can deploy a different user pool for a different environment and have a different set of users. We need to pass a different one each time, so we'll just create a dev1 here. Since we created a set of new code in the auth directory, we'll need to add it to the package.yaml so that it gets packaged up and pushed into S3. Otherwise, our auth function wouldn't exist. So just add auth in to includes. So this is our get profile function, and what we need to do as well is add in an authenticators.yaml file. So we need to declare our Lambda function, our auth Lambda function. This one has no endpoint. It just gets executed by Cognito, so we'll just, or API Gateway first, which will then go to Cognito and double check everything else. So we'll just call that bearer auth. And we reference our bearerauth.main function in the auth folder. Now for any function that requires authentication, we go to that YAML file, and under HTTP, we just add an authorizers element at the same level as cores and method. Just insert it into here. And we give it the name of the auth function. It's as easy as that. Next, we'll run the functions, unauthenticated and authenticated, and we'll see how that looks. Just quickly before we do a serverless deploy, I'll just add in the authenticators.yaml file as part of the functions. And then this is the result after running serverless deploy. So we've got a new endpoint here. And we've got our bearer auth function and our get profile function. Okay. Let's take a look at what's actually in the AWS console. Again, I've clipped the URL bar, so we can take a look, and the cursor will be slightly off, but that's all right. So we see my app dev user pool, so it's got a naming convention. See the pool ID, the ARN to the pool, and some of the things that we set last time. So right now we've got known users. And we've got our password policy, so everything's checked off, minimum of 10 characters. And we created one app client ID. And we've got the callback URL. So the callback, once we authenticate, is going to hit our local host machine. This is for testing. Normally what I do is actually I have the callback URL as localhost and my domain for that environment. So since we're not building a front end, what I'm going to do is create a check for a existing domain. If it's not there, it's going to create one. So we can use it for a hosted UI. Amazon provides a hosted UI for us to do login and registration. Just for the purposes of this demo, we can actually use their SDK for the front end in order to log in. But we don't need to do that. And in this page, you can customize their hosted UI. For a streamlined experience, I suggest that you actually just use the SDK. That way you can customize the flows however you like. Every experience is different, and experience is a part of the application. Cool. So I'm going to do a curl to this endpoint now. Now that we've set an authorizer on it, it should come back with an unauthenticated error. There we go. We got unauthorized message. That's what we expect. And in this case, there are two ways to authenticate, but we first need to register a new user. In this first part of the video, I'm going to do the authenticating code path, and we'll do the implicit path later, which is of type token, as you see here. So this is the AWS documentation. We just fill out our domain, which is the one we created earlier, and our app client ID, and our callback URL. Now the callback URL has to match. And in the code, I put the localhost instead of mydomain.com.au. So that was the other change that you didn't see behind the scenes. Okay, so we have known users as we saw earlier. What I'll need to do now is register for a new user. Just put in my name, tony.trong, and my email address, and some password. If you recall from the previous code, it's going to send me an email message with the verification code. I'm just going to pull that out from my phone, and then we'll stick it in here. Okay, so that actually hit localhost. That's fine. That's the redirect. If you look at the bottom, we've got the localhost get request in the network tab, and we've got a code. In the OAuth flow, what we're going to do is we can make a post request with that code. I'm not going to do it here, but that post request, if we send in the code, we're going to get back an access token. See, we have implicit grant and code grant flows. If you take a look in the user pool, we can actually see that I've actually confirmed and verified. And this is where we actually pay for the Cognito service. So I'm going to sign in again. Sign in again properly. And you see that localhost at the bottom of the network tab. The callback equals code equals some number. And that's the initial request on the right hand side. But at the bottom there, you see a localhost get, and it's got the code in there. Okay, so let's look at the other one next. All right, for the implicit grant flow, first of all, I'm going to do a little bit of house cleaning. We got to change the package to python-jose, and the urllib.request needs to change to import as request. This is a Python 3.7 specific dealie. Okay, cool. So let's sign in again, and this time I've changed the URL type response_type equals to token instead of code, and this will give us an access token once we sign in. Okay, and our callback is to localhost, and we've got an ID token and an access token. So for our testing on every environment, if you want to log in with a token to make API calls in the back end, you can do this. I'm just going to search for the access token bit and pull it out. And it expires in a day. And it's separated by a couple of dots for each section. You can use JWT decode online to see what's in it. It's what we saw before on the right hand side of the code screen. In order to actually use it, we just do a curl with a header, authorization : bearer, space. The space is important because the utils actually parse the space. We paste in our token and we call our endpoint with any ID. And we've got our response, so it's no longer unauthorized. Let's take a look at how we can use the boilerplate to handle WebSocket connections. WebSockets are live streams, and API Gateway now has support on handling the connections for us. It used to be a downfall of Lambda, but now it's fully supported. So I prepared some code earlier, and all I'm going to do now is walk through it. So the first thing we'll do is open up serverless.yaml, and if you take a look at the environment variables, you can see that I've added in DynamoDB host. So this is for the Southeast 2 region. And we need to add these two tags here. WebSocket API name is just whatever you want to name it. And how do we determine the actions? So the routing, and what we do is look at the body.action. I've also ripped out the IAM role statements so that all the functions have this effect. They can all manage connections, and they can all write to a specific DynamoDB table. I did this all here for all Lambda functions so that we can simplify the code a bit just for demonstration purposes. But you can use the plugin IAM roles per functions, and that will allow you to manage the permissions more finely per function. Okay, we take a look at WebSockets.yaml. There's the disconnect and connect handler. That's when the user connects and it'll do certain things. There's a default message in case it can't handle the connect or disconnect. It'll just error or send an error message. And our chat function. So what we're going to do today is build a iconic chat app. You send a message and it'll echo to everybody else. Okay. So we need to import DynamoDB.models. DynamoDB is a library for us to write to DynamoDB, and we'll need DynamoDB to handle the connection IDs for us when a user connects. So to create the table, we need to take a look at this model here, where we have different Boolean types. So we're kind of defining the schema of the DynamoDB table. We extend the model class on DynamoDB and specify the table name, the region. So we get the region from the environment variable if it changes. Otherwise, we default to Southeast 2. And we can specify the throughput of the table and the host. So there's an npm package that we can use that will allow us to run DynamoDB locally in case we wanted to write tests. But we can override that with the environment variable. Okay. So for every connection, there's a connection manager. And from the event request context, we can get the connection ID. Every connection has a connection ID. If the user is trying to connect, we add them to the connection table with add connection. If they're trying to disconnect, then we just remove them from the DynamoDB table. Otherwise, we generate an error. Okay, if you take a look at the add connection method, it's very simple. We use our connection model and add in the connection ID that we got earlier. You can ignore the isReady. That's just kind of a demonstration of the Boolean property. And for remove connection, it does a similar thing. The DynamoDB library is extremely easy to use. I highly recommend it and suggest you look at the documentation for it. Okay, so let's take a look at the actual chat application. We use the Boto3 library to create a connection to API management, our API Gateway Management API. That's a new thing in Boto3. And what we're going to do is we're going to do a scan on the table. So we want to send a message to every single user. We get all the IDs. Then we load the body element. And it'll have a message in the body element. And we'll send that to every single connection using the post connection method. And then the Lambda returns successfully. So that's all it really takes. API Gateway does the heavy lifting for us. And we just deal with the logic itself. So in the scripts folder, I've created a method to create the table manually in case a table doesn't exist. So if I want to handle a bunch of different idempotent DB schemas, that's where I do it. You can create it in Terraform, or you can create it in manually, or you can create it in CloudFormation. But I believe that code schema changes should be managed inside the code itself. And then we can use CI/CD to run it properly. Just make sure your scripts are idempotent. So here we cat the .env variable. I'm going to override the DynamoDB host to be the region endpoint. I'm going to connect to my AWS account. If you change the .env to use the localhost, then you can use a number of libraries out there to simulate DynamoDB locally, but it's never quite the same. Okay. So I'm going to run my sudo migration scripts, just using Python module run. And that should connect to the Southeast 2 endpoint and create my table. Then we're going to do a deployment. So in the default configuration here, there's no private VPCs and no private subnets for demonstration purposes. We'll definitely tackle that in a more secure manner in a little bit. Let's let this deploy. We'll get back. Okay, so if you go to the README in the boilerplate, you'll see that if you remember, we had the JSON object. The action is the route. And if you install WSCat, we can actually connect directly to the endpoint and test it out. So that's a neat little tool on Node. So once we've deployed, you'll see a WSS endpoint. So it's a secure WebSocket endpoint right there on endpoints. So I'm going to connect to it in 2 different terminals. And once we send a message on one of them, we'll see it in the other one. So if you recall in the code, the action is the route, and we enabled that as chat, and it's looking for the message body. We're going to send hello world. Let's check the other terminal, and we got hello world. That's it. Let's see how we can make that a little bit more secure in the next section. Alright, if you managed to make it this far, I think now you are fully armed to the teeth in order to start creating your own business applications. What I wanted to do now is focus on the boilerplate code that I have publicly available on GitHub. Feel free to use this as you please. There's a couple of additional things in here that's not in the course, and I'll walk through them really quickly right now. So when we did our cognito authentication, we had bearer auth in. But now I have some authorization in. So this piece of code will check if the user belongs to a certain group. You can see that here. In the custom group auth, we check the claims cognito : groups and make sure that they belong to that group. You'll also have a post confirmation hook. Now a Lambda hook is something that fires automatically without you explicitly calling it. Once the user has joined the group, we can fire off some custom logic. We also have WebSockets. So in the WebSockets folder, we take a look at the main functionality. We handle the users connecting and disconnecting. And if it's not one of those, and it's not in one of the routes, they'll get a bad request. There's an example echo in here as well. Feel free to read that through your own time. What we do need to look at is the serverless.yaml file. And here we name the WebSocket API, and we give it a route. So in the JSON request, once they've connected through a WebSocket connection, they need to have the action item in their JSON object. Let's take a look down here. We go to the WebSocket connection example. Here, action equals to echo. So in our main.py in the WebSockets file, folder, there's an echo action. And then it'll just echo back hello world. And we can test that here. Finally, our API gateway, we might not necessarily want AWS to name it the random name it has. So we can use a plugin here called Domain Manager. Now we purchase the domain and we check out customs.yaml and set a certificate for it. We can use this plugin to set a custom domain for our API gateway endpoint. For example, dev.mydomain.com.au/API. And you'll see /API here. And whatever our subdomain is. For example, dev or staging or production. And in order to run that, the instructions are also in the README. All you need to do is once you purchase the domain and created the certificate, you can use serverless create domain and serverless deploy. That should set up your API gateway. I've already got some Terraform code in there as well to help you handle that. Here we go. Just be careful that there's currently a bug in Terraform. When that gets fixed, I'll update this code to handle it completely. And that's it for this course. Again, thank you very much for taking the time to go through it, and I hope this helps you.